All right, hello, welcome back. It's 7.2, sample proportions. Let me just take a moment to remind you that chapter 7 is full of vocabulary that you don't know. Go back to chapter 7.1. Review the vocabulary from there. The first vocabulary term that you may not remember is this idea of a sampling distribution. Go back and consider, what is that? Remember, with different samples, we're going to generate different sample statistics. Different samples give different statistics. Not every poll is going to give you the same estimate for what proportion of people are going to vote for this, that, or whatever. So different samples give different statistics. And the idea of this sampling distribution, that shows all the values the statistic could take, right? Because there's a population, there's some true value. We don't know what it is till election day or whatever decision day, but we can estimate it beforehand. We can say, okay, maybe around here with some level of confidence, depending on things we'll talk about later. So the idea here is when we're dealing with proportions, and first you might consider what kind of data was going to give you a proportion. Something where somebody says yes or no. Somebody says this guy or that guy, this lady or that lady, this product or that product. What kind of thing is that? That's a qualitative type of data. Depends on a quality, a yes or a no, a this or a that kind of thing, right? Generally, we're going to be interested in, yes or no. Choose an SRS of size n. Okay, we're taking simple random samples of size n from a large population with population proportion p. Remember, that's the truth. We don't know it, but maybe we do, but generally we don't. That's why we try to estimate it, right? With polls and, research. Let p hat, recall p hat, that's got a little hat on it, be the proportion of the sample. So p hat, recall, is your sample proportion. And, p hat, that changes. P hat depends on what sample you take. And you take a different sample, you get a different statistic. That thing I keep saying over and over. And we have here some values. The mean of p hat is p, and the standard deviation of p hat is square root p, 1 minus p over n. And with the z statistic, there's your z value. So the idea here is, under certain conditions, we know something about p hat. If I had you in person, I'd do a little deriving of these two. In fact, we can derive these formulas from your favorite, those ideas back from chapter 6 dealing with combinations and transformations. Because what is a proportion? It's a bunch of people saying yes or no. It's a binomial random variable divided by the sample size. Think about that for a second. If I see you in person again, I'll show it to you on the board. But for now, it's not a big deal. Under certain conditions, we're going to say that p hat is distributed approximately normally with a mean of p, standard deviation, square root p, 1 minus p over n. Not to worry, that is all on your formula sheet. On your formula sheet. On your formula sheet. So those things are on your formula sheet. You don't have to memorize them. They're there for you. What you're going to have to memorize are those certain conditions. That sounds dubious. So what do we see here? All right. Well, in the middle of all the p hats we could get is the true value p. But what did we call that when the mean, or look at that, the mean of p hat is the true value? We call that unbiased. We'd say that p hat is an unbiased statistic. What does that mean? Does that mean p hat hits the target every time? No. You can go 538, look at the final predictions, go look at what happened for Missouri. Some values higher, some values low. They got it pretty close in Missouri, but on average, tend to get it pretty close. And that's true, that doesn't account for polling error. Understand that does account for sampling variability. What these sorts of polling error, the way you took your sample, the way you're asked your questions, that is not accounted for here. We'll talk about that separately when we get to confidence intervals a little later. So what do you see happens here to the spread as the sampling distribution of n increases? So the idea here is as n goes up, the standard deviation of p hat is going to go down. More specifically, the standard deviation of p hat is, and this you may not have seen anything written this way. What does that read? How do you read that? The standard deviation of p hat is inversely proportional. You might not know that symbol. It talks about proportional. It's a proportionality symbol. Looks like the infinity symbol. You chopped a side off. So it's proportional to 1 over the square root of n. So the idea here is as n goes up, the square root of p goes down. It goes down with the square root of n. So you'll see when we increase sample size by some squared factor, it has a, inverse square root kind of relationship. And we'll see that going on. Not a lot more I have to talk about there. There's just the idea that as we take larger samples, our statistics tend to be closer to the true value. We take larger values, get closer to the truth. Law of large numbers kind of idea. That's a tends to idea though. It doesn't get it right every time. It's not true every time in the long run, in the limit as n goes to infinity. Big number kind of picture here. So you'll find this, that really all we're working with today is consequences of this statement here, that if p hat is approximately normally distributed, and we can go back and use norm CDFs or z-score kind of things, we can find probabilities that sample values would take values here, there, or whatever. Let's go on to the next page. We'll talk about some of the conditions we need. I said under certain conditions. If n is constant, okay, if we have a constant sample size, what value of p gives the biggest spread? Well, sigma p hat, a reminder, is square root p 1 minus p over n, and you might ask what value maximizes that? Calculus folks, you could take a partial derivative of that function with respect to p, or just take a derivative with respect to p, and set it equal to 0. You could find the maximum of that expression, right? Calculus people. If you haven't taken calculus, don't worry about what I just said. The idea is that this maximizes this expression, maximize this expression at p equals 0.5. It turns out if you put p equals 0.5 into that expression, that's what makes it the biggest. And you could go to Desmos or something and make a little slider and slide it around, or you could take my word for it. What must I show in order to find the standard deviation of p hat? All right, so we had some conditions earlier, and it's really whatever it just says down below. To find the standard deviation of p hat, we needed to take less than 10% of the sample. We either need to be sampling with replacement, or we need to be sampling less than 10% of the population. That's usually what we're going to be going with. Sampling less than 10% of the population, we call that the 10% rule. We say that little n, that is the sample size, has to be less than or equal to the population size divided by 10. Sometimes we'll write that as the 10% rule down below, n less than or equal to 10% of capital N. And I think that's goofy to write. I don't like writing mathematical expressions with percentages, but if you do, go for it. I'm going to usually write it like this with the division sign. So we need that. What does that do? That gives us, well, sampling with replacement, that gives us, write it in another color. What does that give us? If we're sampling with replacement, we put it back in. What does that say to the probability of success every time? If we're putting them back in or we're taking a small amount, that's going to give us independence. Remember, we needed independence to be able to calculate the standard deviation of p hat. What must I show? You must show independence. And you show independence by saying, generally, you're going to sample less than 10% of the population. Okay. So we have that check for the standard deviation. And to show that it's approximately normal, and we saw this with the Desmos app, remember the little balls falling? As we took the number of rows higher and higher, you saw that distribution started to look kind of like the normal distribution. We need to see that NP and N1 minus P is at least 10. That is the expected successes and failures are at least 10. We need that to kind of wave our hands and say that this distribution is close enough to a normal distribution to be able to use that approximation. And that approximation makes our life a lot easier because we can use a z-table, we can use norm CDF, we can use those same kind of tools we developed in chapter 2. I've got like 2 examples from here. You're going to find that this is a shorter unit, 7.3. It'll be a little longer for us. So our big example, about 75% of young adult internet users watch online videos. Great. Suppose you contact suppose that a sample survey contacts a simple random sample of 1,000 young adults. I'm going to put N by that. That's the sample size. And calculate the proportion P hat in the sample who watch online video. Okay, so first off, you take a sample of 1,000 people, you're probably not going to get exactly 750 people that said yes. There's some variability. Some might say yes, some might say no. It just depends on who you call. It'll probably be close to that, but there's some variability around that truth. What is the mean of the sampling distribution of P hat? My gosh, there are a lot of words in this unit. You need to know how to turn that into symbols. Mean of P hat. The mean of the P hats is equal to the true proportion. From our first page, we say that, well, on average, P hat is equal to the truth. On average, it tends to get it right. We didn't justify that to you. I can prove that to you if I ever see you in person again. What is that true proportion here? It's 0.75. Works better when I have the whiteboard and I don't want to get out the cameras. So number 1, there you go. Number 2, find the standard deviation of the sampling distribution of P hat. Check that the 10% condition is met. So number 2, we need to check that N is less than or equal to capital N over 10. Well, here our sample size was, young adult, our sample was from young adult internet users. How many of those are there? What's the population size on that? How many young adult internet users are there? I don't know, like a billion? I don't know. A lot of them. A lot of them. So we took 1,000 people here, less than or equal to capital N over 10. So I'm going to put a little question mark. We need to check that that inequality is true. We can rearrange that inequality, multiplying both sides by 10. And all of a sudden, then the statement becomes N is greater than 10,000. Well, is that true? Yes, clearly more than 10,000 young adult internet users. Great. Cool. Oh, I didn't find the standard deviation. Gosh, I gotta actually follow the formula. Standard deviation of P hat equals square root P 1 minus P over N. Here, that's going to be square root 0.75. That's a probability to say yes. 0.25, probability to say no, over 1,000. Get out your calculator. Make sure you can do some elementary arithmetic. 0.75 times 0.25 divided by 1,000. And I've got an answer here of 0.01, let's say 4. Okay, and what does that mean? That means that we're usually within a percent, on average, the value, our sample proportion is 1.4% from the true proportion. Let's say, what does that mean? On average, our sample proportion, our sample P hat is 0.014, that is 1.4% from the true P. Cool. Watermelon colors today. Number 3, is the sampling distribution of P hat approximately normal? Okay, to check for approximately normal, we got to check that NP is at least 10 and N1 minus P is at least 10. Well, we know those values. We talked to 1,000 people, probably a success 0.75. That's 750. That's more than 10. And conversely, if 750 people said yes, then that's going to be 250 people say no. That's also greater than 10. I can do subtraction because if they said yes or said no, that's how all these are going to work. So since those are both at least 10, yes, we can say p hat is approximately, and we're going to write that little approx over the tilde, approximately normal. Mean of, what is it, 0.75, standard deviation 0.014. A statement like that, which I'm going to highlight in orange, is really important. We need to be able to make a statement like that. Say, hey, this is the variable, this is how it's distributed, and if I know these values, then I can plug things into a norm CDF, I can draw a picture that shows that I understand the situation, all that fun stuff. All right, and then number 4 is a little, it's like a ACT kind of problem here. They love this one on multiple choice. So by number 4, just go ahead and put AP, multiple choice, guarantee. I guarantee you're going to see this one on the test. They love this question. If the sample size were 9,000 rather than 1,000, how would this change the sampling distribution of p hat? Well, notice that the mean of p doesn't seem to depend on, the mean of p hat doesn't depend on n. So the mean won't change. But what does depend on n? Sigma p hat. Well, sigma p hat old, the original one, was, 0.75, 0.25 over 1,000. Well, the new one, sigma p hat new, is similar on top, or the same on top, 0.75, 0.25, but on the bottom, I'm going to write it as 9 times 1,000. Why have I written it as 9 times 1,000? Because what is 9? That's a perfect square. You're exactly right. So whenever you see numbers like 4, 9, maybe 16, 25, or 36, understand that that's going to mean making the spread 1/2 as big, 1/3 as big, 1/4 as big, 1/5 as big, or 1/6 as big. Right? So if that's what we multiply n by, that's what we're going to multiply sigma p hat by. So there is that relationship I talked about earlier, specifically that inverse square root relationship. So if we go up by a factor of 9, put a 9 down there, what is a square root of 9? Square root of 9 is 3. This is going to go down by a factor. You can pull that 9 out front, write it as 1/3, and then what's left behind is just the old sigma p hat calculation, 0.25 over 1,000. That is that. So I can make a replacement, I can make a substitution, and write that sigma p hat new is 1/3 of sigma p hat old. More succinctly, I could say that the spread decreases by a factor of 1/3. Great. Knowing that inverse square root relationship is going to be handy, I might, if you forgot your squares, you might take a moment to write those down and remember that relationship. I don't know. You should probably know those. What do I have? I think I have one more for you, and I think we could use our calculator a little on this one. So similar sort of setup. The superintendent of a large school district wants to know what proportion of middle school students in their district are planning to attend a 4-year college or university. Suppose that 80% are. That's going to be the true value. That's going to be P. What's the probability that a simple random sample of 125, that's N, will give a sample proportion of at most 75%? Oh. P hat, what's the probability that P hat is at most, that's going to be less than, technically equal to, but continuous distribution. The equal to value goes to 0, but whatever. So I need to find a probability involving p hat. Well, before I can listen to this, write it down. Before I can find a probability involving p hat, I need to establish p hat's distribution. All right, so let's first establish the distribution of p hat. We could say, well, what do we know? The mean of p hat is 0.8. And sigma of p hat is square root 0.8, 0.2 over 125. Remember, I can only do this formula. What does the 10% rule say? It says my sample size has to be less than 10% of my population. So here, I know my sample size is 125, less than or equal to capital N over 10. How big does my school need to be? My school needs to have at least 1,250 people in it. N needs to be at least 1250 for this all to work. And we hope that that's true because it said large school district. Large school district hopefully means that our sample size is sufficiently large. Excuse me, our population is sufficiently large. When we put that in our calculator, I don't know, what do we get? Let's put it in. Square root 0.8 times 0.2 divided by 125. That's not one I can do in my head. Maybe I could. I could get close. 0.0357. Okay. So we know it's mean, we know it's standard deviation, and now we have to decide, well, is it normal? Approximately. And we've got to check, well, what do we have to check? We have to say here is NP, is that at least 10? And N1 minus P, is that at least 10? So what's that going to be? That's going to be 125 times 0.8. I don't know, what is that? 100? 100 sure is greater than 10, and the remaining 25 would also be greater than 10. So at that point, we can say, okay, p hat is distributed approximately normally. I'm going to put a little approx over it with a mean of 0.8 and a standard deviation of 0.0357. So we now know about the mean and standard deviation of p hat. And I'll write the symbols down below. That's the mean of p hat, and that's the standard deviation of p hat. Great. Now we are prepared to finally answer this question involving p hat. What's the probability it's less than or equal to 0.75? Well, you could draw a picture, right? This is a chapter 2 question. All of a sudden, we know that 0.8 is in the middle. We have a spread of 0.0375. So if we're talking about 0.75, we're talking about something down here. 0.75. We're talking about some little area down there. How can I find that? I, at this point, would break out my calculator and use a norm CDF. Lower bound is something like negative infinity. Practically, that's a bunch of 9s. Upper bound is 0.75. Mean is 0.8. Standard deviation 0.037, and it's going to run out of space, but 0.0375 over there. I'll label over those lower, upper, the mean of p hat and the standard deviation of p hat. And when we put that in our calculator, remember we're going, I'll turn on my lamp, sorry. We're going to go second vars, get our distribution menu up, go to normal CDF, lower bound, that's fine for negative infinity, upper bound 0.75, mean of 0.8, and standard deviation 0.0375. Some people, oh, excuse me, that's not right. Is that right? 357. 0357. Sorry, I transposed the 5 and the 7 I wrote the first time. Some of the clever among you might be saying, isn't the lower bound 0? Well, yes, in the real sense, it is 0. But since we're saying it's approximately normal, we're making some, we're making a little bit of waving our hands, saying, oh, it's close. It's close. You'll find if you put 0 there or negative infinity there, the answer is not actually going to be that different, because to get all the way down to 0, we're talking about like 20 standard deviations below, and there just isn't much between 20 standard deviations below and any further than that, really. So we put that all in, hit enter, and we get an answer 0.0807. Put a little box around it. About 8% of samples would be that low. The truth is that 80% of kids would say yes, but different samples going to give us different results, and some extreme samples, the 8% most extreme samples on the low side, are going to give us a value less than 75%. And now you've got these 3 dang symbols that you have to know the difference between. P is the population proportion. P hat is the sample proportion. And the mean of P hat is the mean of the sampling distribution of the sample proportion. There are a lot of words in this unit, and you need to know the vocabulary. Go back. If you're struggling with vocabulary, have 7.1 out as you're doing this. It's in the same packet. Flip around. Homework's not bad on these. 7.3 is going to be a little more. That's it for today. We will see you next time. Look at that vocab on the very front. Very nice for you. Use it. See you guys.